A very good morning to our guest, Professor T.R. Rao. Welcome, sir.
Thank you.
And good morning to all students and participants here. And today here we have Professor T.R. Rao, and now he needs no introduction to you people because we all have privilege to hear him twice. And now we are lucky to have it one more session with Sir on test of hypothesis and basics of SPSS. So without taking much time, uh, I would like to invite Professor T.R. Rao for giving his talk. Over to you, sir.
Okay, thank you. All right. So, dear students, participants, you have seen me already giving lectures over the last 3 lectures or so, and this is my last and the final lecture, and this is probably the most important one because this really gives you the crux of statistical testing. How do you go about testing a hypothesis? And how do you decide whether an observed effect is significant or not? Okay, so please pay attention and listen very carefully because the time is limited. So I can't go over again and again, although I will try to. But if you have some questions, you may put it in the chat box so we could take up during the question answer period. Okay, so let's get going. I'm going to my presentation and so you won't have any distraction. I will share the entire screen. So you see this beautiful blue sky. Hello? Can you see the screen?
Yes, sir. We can.
Okay.
Yes, sir.
Okay. Well, ready to go. So today's topic is hypothesis testing. Okay. So in statistics, of course, nothing happens unless you propose a hypothesis based on your observations, of course, and go about testing it. So how do we go about testing is the theme of today's lecture. Hypothesis testing. Let us look at some hypotheses. You already had some idea what exactly hypotheses are and how they are testable or not, and all those basic principles of hypothesis. I'll take up directly some examples. Let us take one example. So we are proposing, based on our observations perhaps, we are saying that in saline soils, plants do not yield as much rice as grown in normal soils. This is a problem in places like Kerala, where in the backwaters, the soils might be saline and crops might be different. Then genetically different varieties might be flourishing there. We don't know. Another example. Our Baba Ramdev has been making a lot of claims about everything, including cure for COVID. So this is a claim he makes. So so we can take that as a hypothesis and go about testing it. Somebody suggests that while you're working, you have some nasty discussion or fight with your boss, and suddenly your BP goes up. Simply says, do pranayam, cool you for 5 minutes, everything will come down to normal. That's a hypothesis. That's a hypothesis which 50% of the students may not agree. Dr. Wattle will sort of give some hint. Is this true, ma'am, in your classes?
Sorry, sir. Yes, I do agree.
It does happen.
Okay, so yeah, so we can still test it, because not all boys might believe in your statement. Okay, finally, a little politically sensitive hypothesis. So these are testable hypotheses. Okay. Okay. I'm going to very clearly go through one hypothesis so that we'll see where we have some problem. See, whenever I ask you something, your statement is not 100% sure kind of thing. So let me ask you a few things, then I assume you're answering me. Um, are you sure it's going to rain today? So you'll say, definitely. Are you sure? Yes, 100%. Or you might simply say, probably. What do you mean, probably? Well, there's a 50% chance of rain. Okay. You think you'll pass in the exam? I don't know the way I'm studying. Probably. What are your chances of passing? Maybe 30% chance that I'll miss. Things like that. You're making statements where there are statements where you are 100% sure. There are statements that you are making of which you are not too sure. Then, without your own knowledge, you are giving a percentage value that you might be wrong. Okay, that's what statistics hold on to that. That might be kind of a thing that you want to hang on to so that later you will not be accused of saying, well, you said it's going to rain, so I went without an umbrella. You see what happened to me, these kind of things. Okay, so now let us go through how a statistician looked at this saying maybe kind of things. Okay, I'm just taking a hypothetical example. All right. This is about possibility that in lowlands Andamans, they are relatively rare pancreatic cancer, but population living in the hills, they have some regularly add some head and their diet, so they seem to have less frequency of pancreatic cancer. So that's an observation. What's the hypothesis now? This rare herb has some chemical capable of suppressing cancer cell proliferation. As good scientist as you are, you say, oh, that is testable hypothesis. Let us see. You can conduct an experiment, probably on laboratory mice. One control doesn't receive this herbal thing, and the other one receives the Andaman herb, and look at the cancer cells. Now, this is important thing. You find definitely treated group, that is one that has received in the diet the Andaman herb, the cell growth was inhibited by 15%. Now, is this enough to go ahead and proclaim to the world that we have found a cure for cancer? So you have this nagging fact. So are we sure that it is really the effect of this herb that is acting on the inhibition of these cancer cells? How sure are we? Now look at this. What I want to say is this. After all, the inhibitory effect was only 15%. It's not as though 50%, 75% are total suppression. No, it's just 15%. Is it not possible that just it occurred, this inhibition occurred by chance, not necessarily due to the effect of this herb? So, if there is always a chance that something might come out, how do we know whether we can make a definitive, believable statement about anything? So, in order for us to take into account that the effect of any treatment, here it is the herb, should be significantly higher than that could occur by chance alone. very often we see that people will simply say, it's just luck, he just passed. By chance, he was able to get it. Some such thing. So there also you are talking about chance, although you are not quantifying it. So the question asked was, what is the probability that the observed result was due to chance alone? So here is the one that came up with this uh, proposal, how to evaluate this. And he is one of the, as I told you before, he is one of the founders of population genetics, and he's a big, giant figure in statistics. Okay, just read this now. So we have to set up a hypothesis and see how we go about setting up. There is what is called a null hypothesis. What is a null hypothesis? In statistics, there is no way to test something that definitively happens. You simply propose that it doesn't happen, okay, and then you prove that's not true. You got the opposite, right? So now you with this reference to the head, you simply say the head has no effect. That's your null hypothesis. Null means no. Okay. So the girls fare better in biology than boys. There is no difference between girls and boys in the probability of doing well in the biology classes. So you propose a null hypothesis, and statistics will allow you to reject that null hypothesis if it is a significant. Okay, good. Keep this in mind. That's why, because everybody proposes a null hypothesis. So null hypotheses are like this. Okay, so these are actual observations. See how the null hypothesis goes. Males and females do not differ. Symbolically, we show mu, that is the difference, the response to emotional stress in females is no different from that of the males. Tumor growth is the same in drug treated and controlled mice. Remember, we are looking at a measured parameter for which we are looking at the mean values for comparison. Again, Punjab versus Bihar in relation to the number of eggs produced, the mean number of eggs produced. That's why we are putting this mu, population mean. We're not concerned with the sample mean. Sample mean, it's very evident whether it's present or not, whether it's equal or not. But based on that, you want to speculate on what happens in the population. Here, you want to test if there is a strong association. Now, so go about proposing that there is no association. Then see if you can reject that hypothesis. So that's how you go about setting up a hypothesis. Okay. There is another interesting aspect of setting a hypothesis. Look at the statement. Within the same age group, cholesterol levels are not different in women and men. Okay, that is that one. Okay. Now look at the way I can propose the same hypothesis differently. Within the same age group, women have higher cholesterol levels than men. Maybe my observations led me to conclude like that. So I can set up a hypothesis this way rather than saying both are same. Okay. Because now I feel that women definitely have a higher cholesterol levels, age group being the same. So now the hypothesis would look like this, the null hypothesis. now you say women have either less or equal to men, but not more. All right. So this is a way of proposing this one kind of hypothesis. This is another kind of hypothesis. Here we are talking about inequality. Okay. So these two have names. Remember, each normal distribution has two tails, one on the right side, one on the left side, where the tails extend. Okay. So let us call them as T1 and T2. In the first one, we are only saying that they are different. It doesn't matter whether one is higher than the other or the other way. Just as long as they're different, we are satisfied. But here, the proposal is that it has to be definitely women who will have the higher cholesterol levels. So that means women having higher levels means that we are only interested in the higher side, not in the lower side. Correct? That's why these two have different names. This is a two-tailed hypothesis because it could be higher than the mean value of the other one or lower. Okay, whereas this one is one-tailed hypothesis. We are only concerned if it is lower or equal. We are not concerned if it is more than that. Okay, and that makes a difference later. Okay, we'll come to that later. And quickly, there is a difference between statistical hypothesis testing and scientific hypothesis testing. Statistical, we are simply concerned if they are different. The treatment and controls are different. In a scientific experiment, you have to find out why they are different, and you might want to do an experiment. So we ask these questions. So it got you some idea that seed number could be different because the nutrient levels are different in these two soils. So you can conduct an experiment with different levels of nitrates and phosphates in your soil, in your laboratory, and growing them. Then you proved the point. Okay. So this is another thing that is, we are testing the hypothesis that holds for the population, but we are doing that based on our sample. Let it be very clear. Because if you know the true population value, there is nothing to test. You simply make a statement. If you want to test the entire population, if you take all human adult population, the normal heartbeat is going to be 72 per minute. There's nothing to test. But if you took a random sample and you want to see if the random sample is representative of the population, you want to be sure what you got will definitely project what happens in the population. So here you can see that our sample mean is trying to estimate population mean. Our variance, sample variance is trying to estimate the population variance, and our standard deviation, sigma, the population standard deviation. Okay. Now, this is the crux of the problem. You don't know the truth, real population value. So you might be making a mistake when you reach conclusions. Let us just imagine an alien from elsewhere, some other galaxy or even Mars, somebody comes to Earth. Okay, he doesn't know the true value of the normal heartbeat rate, the pulse rate. He takes a sample, a random sample, okay, and measures their pulse rate. What he gets is truth or not, we don't know. He doesn't know. We know. He is new to this planet. Maybe there the hearts don't beat. We don't know what it is. But out of curiosity, scientific curiosity, he measures it, and then he has a sample value, but he doesn't know the truth. So we are in the same situation when you do this with a sample. We have values of the mean and standard deviation, but we don't know what the true sample, the population mean and standard deviations are, in the entire population. When you don't know, you might be erring, means making mistakes. Okay, you might be rejecting saying the truth. Okay, or you might be accepting a falsehood. Let us see what these errors that we like to make. Okay, we have tested this. Drug A has significant effect on serum cholesterol levels. There are 4 possible conclusions you can reach after this testing. Follow these, all these 4. Drug has a real effect. That means population effect, it is true. And we also found the same thing in our sample also. Second possibility. Drug has really an effect when you look at the whole population level. But unfortunately, our study concluded that didn't have any effect. It's possible because talk about random chance. Okay. Third, the drug has no effect at all. If you look at the entire population, has absolutely no effect. But somehow, based on your small sample, you have reached the conclusion, same conclusion. Good. That means you accepted your sample let you accept as truth the population mean. But you could make the mistake also. When the population wise there is no effect, your sample made you conclude that it has an effect. Okay, this is what happens when people try to cheat you, companies, by saying it has a significant effect. What is the sample size you did this experiment testing? I say, oh, 20, 40, 50. But you want to use this entire population, thousands of them. How do you know if it works? So these are the 4 possibilities. Now let us carefully look at in which of these 4 have we reached the right conclusion. There. Because the drug has real effect and we also found the same thing. There you have. It has no effect and we also concluded there is no effect. Right? How about conclusions 2 and 4? We made errors here. When it has a real effect, our study concluded that it didn't have any effect. We goofed. Here we rejected a true null hypothesis. Our null hypothesis, true, it was true. But you rejected it. Again, the 4th one, it has no effect, but the study concluded it has an effect. There also you made a mistake, right? Error. Both are bad. So, these are the 2 errors we committed, or possibly we could commit. You will not commit both, of course. You commit one of them. What are those? The error of rejecting a true null hypothesis. This is the first error. The second one is error of accepting a false null hypothesis. This 4th one. When there was no effect at all, which was false, you accepted that it has an effect. So, in any statistical treatment of data, in any experiment you conduct, either of these errors is likely to happen because you are trying to estimate population values based on your sample values. Okay. Have you understood this now? Let's see. So we'll test with an example. We'll consider from judiciary first. We will go to courts and the jury and the accused and all that. Okay. Okay. If person is brought to the court for judge to hear both sides. And normally in most countries, the law says a person accused is is innocent until found guilty by the court. Okay. So a null hypothesis, that guy is innocent. It could be true, it could be false. That means he might be guilty, We don't know, but we assume he's innocent. Now the court appoints a jury. We don't have jury system, but many countries do. So jury deliberates on all the points they have heard from the prosecution and the defense, and they reach a conclusion. They could say he is guilty, or they might pronounce him innocent or not guilty. Okay. So let us see what are the errors that we have committed. This is correct because he is not guilty. That's true, and they also jury also found they are not. So this is a correct verdict. Okay, that's also correct verdict. Okay, he is found guilty when he is actually not guilty. I mean, he's okay. So this means now the opposite ones will be that they give a wrong one. Okay, when it is true he is not guilty, the jury pronounced him guilty. Here also it's wrong, right? So in any possibilities, there are possibly two possible errors you could make, either of them. These have names. The error of rejecting a true null hypothesis is called type 1 error. Not because I mentioned this first, but it's invariably called the type 1 error. Okay? And the error of accepting a false null hypothesis is called type 2 error. And they have symbols also for this. Type 1 error is alpha, and type 2 error is beta. Statistics invariably, when you see alpha error, you know they are talking about type 1 error, that is error of rejecting a true null hypothesis. Okay, and beta accepting a false null hypothesis. I will go to, just to reinforce this, I am going to take up a clinical example. The patient has AIDS because you have a bunch of patients suspected of having AIDS. You bring them to for testing center. So with the assumption he might have. So null hypothesis he has. Again, the two possibilities, either it's true or false. Now here that is not the jury, but the test, the test kit you are using to test. The test turns positive, or it could be negative. So again, you can see the errors that could happen. This is the type 1 error. They had AIDS and your test goofed and they declared as healthy. That is dangerous because this guy will go home and infect his wife and any other woman he would come in contact with. Right? And this one, healthy patients were wrongly diagnosed as having AIDS. That is terrible. Your test made him so feel miserable that he has AIDS and his wife will just desert him, maybe go for a divorce and all those things just because your test goofed. So these are the two errors that happen. Okay. So these you can call them as false alarms. Okay. Because when he didn't have, it gave a false alarm saying, watch out, this guy has it. Okay. As opposed to this, what would you call this one? This error, something equal to this one. I pause here with my students and ask to think of a term that you could use before this for this one. It is called failed alarms. The test should have come up buzzing, saying that this fellow is wrongly diagnosed as healthy. Watch out, he has AIDS. So here it was a false alarm, here it's a failed alarm. You understood now what is type 1 error and type 2 errors? Here is a quick quiz, picture quiz. Okay, where is type 1 error and where is type 2 error? Okay, I gave you enough time. Type 1 error. She is rejecting a true null hypothesis. You see the bulge. She is pregnant. And she says you are not pregnant. Unless she was hiding a pillow behind her throat. Right? So, this is type 1 error. Here, obviously, this dumb doctor says you are pregnant. And so he's committing a type 2 error. Okay? So, in AIDS or any other testing procedures, we use sensitivity and specificity. I mean, normally I wouldn't go into details with this but we are living in a COVID testing times. So I thought you might want to know this terminology. Sensitivity means a patient should test positive if he has AIDS. You can replace AIDS with COVID. Specificity, he should test negative if patient is healthy. Okay, so these are the important things when you come up with a sensitive test or whatever test you call it for diagnosing AIDS, COVID, whatever. So if you apply this to HIV test, but it could be, might as well be COVID tests. Okay, so here I'm defining sensitivity and specificity. That refers to sensitivity. Okay, and the other one refers to specificity. It should test negative if he doesn't have. He should test positive if he has it. So these are the sensitivity and specificity. Oh, you can quickly see with COVID-19. Let us say we have a test that has a 95% chance of detecting the disease if the person has this disease. This is sensitivity of the test. That means if there are 100 patients having COVID, it will miss detecting 5% of the cases. Okay. And 90% chance of correctly indicating that the disease is absent in a person really does not have it. That is specificity of the test. Okay, quickly. Yeah, let me see the time. 8% of the population coming to for a test has the disease, assume in a population. So he can test positive either due to false positive or real positive. Okay. So you can see how the probabilities are worked out. I'll just only let the flow chart explain the details. I won't go into the detail for lack of time. Sorry. Okay. So to test positive for the random individual, you have to multiply these two probabilities. So this guy has the disease and he tested positive, so that is true positive. He has the disease but tested negative, so it's a false negative. You can see the combinations. So our question was, what is the probability that a randomly chosen person has the disease or tests positive? There you go. You have to add this and gives you 0.168. That is 16% chance, 17% chance of will be testing positive. Right? Okay? But remember this now, the only false positives, you don't have unfortunately tested positive in almost 9 cases out of the 17. Okay. Now the question arises. Type 1 error is inevitable because you don't know the truth. You might reject a true null hypothesis. Our alien from other galaxy might reject a true hypothesis of 72 per heartbeat. Okay, because based on his observations, because his sample mean might have come out for 90 or 84, whatever. In our statistical testing procedures, when we do research, when we are testing anti-cancer drugs, when we are testing the effect of something on fish mortalities and all those things, we can never be 100% error free, type 1 error free, because we never know the truth. We could be making mistakes. So you simply say, look, I'm not God. I won't know what the true population mean is. So I'm giving an estimate. I could be wrong by certain amount. How much error will you allow? Somebody who says, the meteorologist says, there is a 95% chance of rain today. So he is allowing for 5% error that he could be wrong. But if he made a 100% saying definitely 100% is going to rain and it didn't rain, the whole meteorology department looks unbelievable, unreliable. Okay, right. So a statistician or a guy doing experimental these things and wants to estimate population values based on your sample values, he says up to this much error I will allow. Beyond that, I will simply say no, this is not correct. And what is that amount of error you have to allow? Is that fixed by the investigator or is there a fixed value? Type 2 error is even more difficult because if this hypothesis is not true, you don't know what the alternate hypothesis is. You have a set of hypothesis, but you don't know if this is wrong. What is the correct hypothesis? You have no idea. Right? So type 2 error, you simply have no idea how much you could be committing. Can it be fixed? Alpha error, are we able to fix it? Beta error also, can you fix it? These are the questions. But you can see that these two errors are related. If you fix something alpha error, you might something invariably automatically set a limit on beta error also. Okay, this I will graphically illustrate to you. Carefully follow this, please, this graph. Okay. Remember, as a rule of thumb, we are allowing for 5% errors in type 1. Okay. All right. So a standard curve with mu value is 30. I don't worry what they are, it's okay. And a standard deviation of 4. We'll set type 1 error at 0.5. This is the 0.5 level, that means we are going to accept. Beyond that, maybe it doesn't belong to our hypothesis. So in statistical parlance, we call this as the acceptance region. 95% of the values. Okay. And beyond this, on either side, will not be acceptance region. Okay, because we set up this 0.5, which means, of course, 0.25 will be here, 0.25 will be on the other side. So those two are rejection regions. You can see marked in the graph also, the normal curve. If this is alpha, this is alpha by 2. We distributed this error either way. Okay, 0.25 and 0.25 here. This is 1 minus alpha, the acceptance region. Now, look at an alternate hypothesis. Why are we doing testing the alternate hypothesis? Because we want to find out if alternate hypothesis is true, we might be making type 2 error, the beta error, right? We would like to see what the beta error is in terms of this graph. Now, this orange curve, which is the alternate hypothesis, we are proposing that it is the mean is actually 42, right? Something like that. Okay, not really 30 that we propose, that actually it's probably 14. So now that curve has its own acceptance regions, right? I'm giving the same standard deviation of 4. Now what happened? This part of the curve of the alternate hypothesis, watch it, as encroaching into the acceptance region of our original hypothesis. This shaded portion of this curve belongs to the alternate hypothesis that mu alternate is 42. Okay, and that much portion, maybe 20%, 30%, whatever, is falling within the acceptance region of our first hypothesis, which is the one we proposed. Right? So whatever is in this region, 1 minus a region, we are going to accept, right? So this portion also values we are going to accept. Oh, we made this mistake because we are accepting certain number of observations as true when it is actually false. You got it? So this alternate curve, normally we don't know, but to illustrate this theory, I'm chosen an alternate hypothesis of 42. Now you can see that if I plot this, part of this orange curve's values, this area, is falling into our acceptance region of our original hypothesis. That means we will accept whatever values are in this. And that unfortunately includes observations from this side, from this one. So here is the situation where you are accepting false null hypothesis, that it is 42 for all these observations. So here you are committing a beta error. Okay. And whatever is left of this curve, these values, okay, if it is total is beta, and this will be 1 minus beta, right? This remaining area. What would that be? This part, what would 1 minus beta be? Just think about it. I'm just putting both together so you can see what's happening quickly by comparison. You see, now I set this acceptance region to 99% and rejection at 0.5. That means I set up this alpha error only at 0.1. I don't want to save 5 chances in 100, but I want to save 1 chance in 100. This means now the alpha value I can set. I am willing to bet 5 chances in 100 on I will let go, or sometimes 1. Now, because in medical clinical situations, 5 is too much. You might simply say 5% is okay. That means you are letting 5% die. That may not be acceptable ethically in medicine. So you might simply say, okay, my testing procedures, I'll take alpha error as 0.1. That means 1 in 100. That's inevitable. By chance it could happen. So I'm accepting that as a type 1 error. Okay. So just to illustrate this, what happens to when you set from 0.5 to 0.1, that means alpha error we have reduced to 0.1. Now see what happened is the amount of beta has increased, right? From this small area to this much. This means the finer the small error term you put, the smaller error term you choose, alpha error term choose, the greater is your chance of committing a bigger amount of beta error. Okay, that's important. So you can see that Obviously, these two are inversely related. You fine tune your type 1 error going to 0, 1 level, then it will be different there. You increase, it will invariably change the possible beta value. I'm saying possible because you never know what's the alternate value. Just as our guy from the Mars or some other galaxy doesn't know what the null hypothesis is. He might be accepting his own null hypothesis, which might be far away from 72, right? So the remaining part, if you take this yellow shaded one, is 1 minus beta. We can give it a name. What is this now? This part? Accepting, okay, or rejecting a false null hypothesis, correct? So you want to keep low the probability of accepting a false null hypothesis. That means you want to keep this as small as possible, right? Because this is unfortunately you're accepting a false null hypothesis. You want to keep that as low as possible, so that the possibility of rejecting a true, false null hypothesis is higher. Okay? This means now the more powerful a test is, the less likely you make a beta error. Okay? So I told you in the beginning that there is no way you can set a beta error because you don't know what the alternate hypothesis is. However, you can sort of indirectly select such parameters like sample size and beta in these alpha levels and all those things such that you reduce this possibility. That's why this 1 minus beta refers to the power of the test, the statistical power of the test. So when somebody says, I have chosen a very powerful test for my data, he means this. He wants to keep this as much as high as possible and minimize this. All right. So I'm just quickly going through. Let's see, I have. Okay, I'll take another 10 minutes, ma'am. Okay.
Sure,
Okay.
sir, sure.
Okay. So now we are armed with our theoretical knowledge of what errors we could be making, type 1 errors, type 2 errors, and what happens when you do all these kinds of things. Let us take a simple example, okay? Oh, we keep coming back to our adult heartbeat. You think I'm obsessed with this Dil Ki Dhadkan? No, I could have chosen some other one. Okay, but this is the most familiar one for everybody, and it's easily measurable in your lab office anywhere. Okay, so the mean came out to 84. Was the sample random? When the population value is 72, how come you got 84? Maybe it's not a random sample. Maybe you chose a bunch of students who were about to take an exam and so their heartbeat went up. Huh? Things like this is possible, right? Your random sample is not random truly. So let us test this hypothesis. Another one, a more tasty one. Okay, so potato chips. Now, what's the null hypothesis here? Because the manufacturer's claim is a null hypothesis. He says the net weight in this potato chips in this bag, huge bag, is 100 grams. This is testable. You can go test by buying about 10 packets and weigh all the chips before you eat, okay? And see the weight variation from 100 grams, okay? So now the null hypothesis is this. Okay, and let us say we have taken 12 samples from different stores and the mean came to 97. Now the question arises, is it by chance that because our sample some small or something, instead of 100 the average came to 97? Or if this is true, Is the manufacturer cheating us by depriving us of 3 grams more of the chips? Right? So that's the question. So we can test it. This is obviously, you will not complain. You will not go to court. You will not go write a nasty letter to the manufacturer if instead of 100 you got 105. Goody, just a few more chips to eat. You will get upset only if it is less than 100 grams that was claimed by the manufacturer on the label. Right? So that's why this is a one-tail test. You are concerned only if it is less than 100, but you don't bother. I'll be very happy if it is more than 100. So now, what do we mean by acceptance region? If you take 20 observations, okay, I'm just showing those 20. Since we acceptance region is 0.95, 19 observations out of 20 should be from mean plus or minus 2 standard deviations, because this is the, remember, mean plus or minus 2 standard deviations will give us 95% of the values. So we chosen 0.95. Okay. Now you can see that 19 out of 20 fall within 2 standard deviations of the mean. Only one is not falling. So this is the oddball. This is because we error, alpha error as 0.05, right? That means 1 in 20 could be outside the acceptance region. Okay. Now suppose now we see now what happened. See, we have 2. So now the probability of region of rejection has increased from 0.5 to 0.1 now, because 2 out of 20, right? So now the probability of committing type 1 error is now 10% instead of 5%. If you set up this hypothesis and then it must be 95% acceptable and a 0.5 level of type 1 error, if you get 2 values, then p-value has exceeded 0.5, right? Then you cannot reject the null hypothesis. This is very important. You are not able to reject the null hypothesis because the p-value, the probability value, has exceeded the limit that you have set at 0.5. Okay, so it has to be 0.5 or less to reject the hypothesis. Now you are not able to reject because the probability has increased to 0.1, that is 10% error, which is not acceptable to you. No, that's too high. Maximum I could allow is only 0.5, 5% out of 100, right? So you are not in a position to reject if the probability value exceeds 0.5. The reason I go into great length with this is the p-value that is ubiquitous in all research papers. They will quote the anti-cancer drug has a significant effect. That means compared to controls. In brackets, they will put p less than 0.5. Okay. Accidents are more common, road accidents are more common in this stretch of the freeway than in other stretches. P less than so and so. So every time they are telling you what is the probability of being wrong and rejecting the hypothesis, right? So they are saying 0.5. The probability could be more based on your observations. So it could be 0.2, let's say. That is 20 chance out of 100. So then you cannot reject the null hypothesis because null hypothesis says no, it is not that hypothesis. So you cannot reject that, right? So this is the principle in which you make decisions about the outcome of your statistical treatment of your data. you assign yourself an alpha error of 0.5, okay? And then you simply say, look, if it is anything more than that, I cannot reject the null hypothesis, right? So when you do not reject the null hypothesis, you are saying, suppose now potato chips problem, okay? When you cannot reject the null hypothesis, that is 100, you're simply saying, although my sample gave a mean value of only 97 grams, but manufacturer's claims are probably true because on the population level, it is still 100 grams. So I cannot reject that hypothesis. Okay? Okay, so we come to the final one, another 5 minutes or less. This is the rule to reject the hypothesis. Okay. Now, based on your data, you have to know what is the probability. In other words, we are working out backwards, right? So how to do that? You have to calculate the standard error. Okay. And then you calculate the p-value. We use what is called a student's t-test. Probably somebody will be giving a more elaborate explanation of this, but quickly to sum up my presentation, this helps us to decide the p-value based on which you can decide whether you reject the hypothesis or not. So we check up the values of the you got the t. T is calculated like this. Okay, your observed value in our potato chips example, the observed mean is 97. Population mean, the manufacturers claim 100, divided by the standard error based on our sample size of 12. We got t value of 3.46. And this helps us to read the probability, whether it is 0.5 or more or less or whatever. Okay. Generally, to read t table, you use n-1 degree of freedom, where n is your sample size. So for 11 degrees of freedom, we read the t table. This is the t tables. So this is the degrees of freedom, and it also gives you specifically whether it's one-tailed or two-tailed. In our case, it's one-tailed. That way you can decide, So then see, this is your 11, sample size n-1, and you go there. You see, you 3.46 you got, right? You just keep going somewhere here, and then you look up the p-value is, p-value is given here. So it is much lower than 0.5, right? It's even lower than 0.1. So now we reject this null hypothesis. Okay. Another way of looking at it is look at the critical value. So in order for this to be significant at the sample size given 12 degrees of freedom, you need to get at least 0.5, right, or less. So the value has to be at least 2.201 or more, the t value, in order for you to reject the hypothesis. Okay. So this is the rule of thumb. That's how you go about doing a t-test, in which you have to see what's the probability of the value you got of 97 being true to the population or not. So the probability came to less than 0.5. So you simply say that's a sample variation because of the small sample size. But I still agree with the manufacturer's claim that the bag has truly mean 100 grams of potato chips. That's it. Thank you.
Thank you, Professor Rao.
Okay.
And
Yeah.
I will now open the session for question answers So in case any participant is interested in asking question, please raise your hand and we'll enable your mic and camera and you can directly pose your question to Professor Rao. Is there anyone?
Ready? Well, the proof of the pudding is when they start using these testing procedures in their own research.
Yes, sir.
Yeah.
Okay, till then, I have some questions in my chat box and I'll ask those questions. One is that terms specificity and sensitivity, aren't they related?
Well, it depends on the type of the test. It's for instance, sensitivity has to refer to the instruments, how accurate it is. But in a way, they are related, but not necessarily in a one-to-one fashion, the relationship. Because everything that is sensitive would be expected to be specificity also is very high, but it varies. Because in some tests, they will say, sensitivity is 0.95, specificity is 0.8. Okay, so it varies depending upon the type of the test and the type of the instrument, the diagnostic tool.
All right.
But these two they have to specify. Any new toolkit that comes up, they have to specify these two.
All right, sir. Thank you. The next question is it possible to know type 1 and type 2 errors in the population?
No, population has only one value. There is no such thing as an alternate value. Population will have a true value, which you don't know. So in the absence of the true value of the population, you can never guess what could be the magnitude of the beta error. You only want to say whatever it is, I want to minimize it. That's all.
All right, sir. Thank you. Another question is, when should we use directional hypothesis and when non-directional?
Okay, you use the directional one when you are convinced that the other side would not be true. Okay, so for instance, in the potato chips one, you don't care if it is 105 grams instead of 100. You are worried and upset only if it is less than 100 because the manufacturer's claim says 100 and you found it's only 95 or 90. You are cheated. So that's a directional hypothesis. You want to test only if it is less than 100. And you keep quiet if it is more than 100, right? So that is how you decide. Now, for instance, if you say that women have higher cholesterol level than men, are you justified in making a one-sided or one-direction null hypothesis? No. Somebody of the other gender will object and simply say, you are making an a priori judgment that women should have higher cholesterol levels. No, you test only two-way. So we could be different. We could have more higher level of cholesterol or lower level of cholesterol. So you could test only if it is different.
Right.
Yeah.
Thank you. What are the, how do you formulate tables like T or chi?
Well, what things have been worked out using those equations that I showed you for T, right? So based on that, they put in the computer and ask you to develop for different sample sizes, different probabilities. So it gives the values and they print the table.
Okay. This is all that I had in my chat. Anyone else who would like to ask any question, please feel free. Raise your hand.
Just to show me that you are capable of asking questions, please, one of you raise a question. Raise your hand. They don't
You
want
did it so well, sir. Where is the scope left?
That's what we are looking at it.
Yeah. Sir, I'd like to take this opportunity to propose officially the vote of thanks. And it was absolutely an amazing lecture like all other previous ones. And I'm sure all the participants were able to take home the lessons. Professor Rao, I just wish to inform you that despite these live sessions, we are uploading these lectures on our YouTube channel for posterity so that whenever whoever is stuck in these topics can reach you through these lectures, and they'll post their questions in the YouTube chat box and you can kindly address them.
Sure.
And another thing that I want to say now that it was your last lecture, so you had amazing slides, amazing examples, and I'm really impressed by the command on your command on even on technology besides biostatistics. So wonderful slides. And thank you once again. We'll again get in touch with you when we start our biostatistics 2.0. Thank you.
Okay. I also want to express my appreciation for these organizers, including Dr. Vatal, for giving me a chance to participate in this in my own humble way. And whatever little I could contribute, it has been my pleasure to do so. And if the students got something out of my 3 or 4 lectures, I would have been very gratified. Thank you very much. And all the organizers, everybody of the whole team, that you have done so well. And congratulations to you.
Thank you, sir.
Bye.
Bye-bye. And now I invite Dr. Shivangi to take the proceedings further.
May I have the permission to leave, please?
Sure, sir. Thank you so much. We'll get in touch with you.
Yeah, okay. Bye, Shivangi.
Bye-bye.